Welcome back to homeschooling. Here we are discussing a new chapter in refraction and lenses. The title of our chapter or our lesson is concave and convex lenses, and these are the titles that will be discussed in this video. So here we are in chapter 18 in Glencoe book. We already did in the previous video the refraction of light. Here we are now discussing the convex and concave lenses, and the next video will be on the application of lenses. Alright, so here we go. So first of all, lenses has multiple applications. Okay, long time ago. So long time ago they used the lenses, okay, for correcting eyesight, as we see here, lenses to correct eyesight, or also scientists like Galileo used for constellation, for example, to looking at stars or at the moon at night. Okay, so they have multiple applications, and of course they are worth studying, lenses. All right, they are very important, especially we'll discuss their importance in our next lesson on the application of lenses. Okay, so let's start here. A lens is a piece, okay, of transparent material like we see here, or in my glasses as well. It's made of transparent materials such as glass or plastic. Okay, so for example, a lens that's thicker at the center, okay, we call it a convex lens. Okay, like the one that we are seeing here, which is thick at the center, we call it a convex lens. Okay, how this convex lens function? When the light passes through such lens, okay, all the light, okay, they pass or they converge. Okay, as we see here, so the light passed through the lens, and all the light passing through will converge to a single point. Okay, so that's a big function or the main function of the convex lens. Okay, so we read it together as the light passed through the common point called the focal point, that we'll talk about it in details in this lesson, the focal point. Okay, after going through the lens, okay, for this reason a convex lens is called a converging lens. It's a converging lens because it converges all the light to just one spot, to just one point. All right, so the second type of lens that will be discussed as well is the concave lens. Okay, as we see from the picture here, we have source of light sending 3 rays of light. When it passes through the lens, the concave lens, look how the light is diverge. Okay, it's going out, it diverge. Okay, so that's a big property of the concave lens, which is in opposite to the convex. So in summary, the convex lens is used to focus all the light to a single spot, as you see here. It's a convex lens, and this is the concave lens. Okay, you see how the light is going and dissipating in the space. All right, so this is a big or main function of both lenses. All right, so let's discuss now in details the convex lens. Let's discuss it in details. All right, so we can go through the text here. So here they are teaching us how to draw, okay, how to draw the image, okay, in case if we have a convex lens. Okay, so how to draw it. All right, so here are the details. So mainly we have the object at the beginning. We have the object, and look where is the image. But how we reach this space, how we reach this image, or how we constructed this image. Okay, so first of all we have the object. I want you to look at the object position. Okay, here we are. Okay, two rays, ray 1 and ray 2, are started from this object, from the top, or the top of the object. Okay, so ray 1 going straight parallel to the principal axis. Okay, so we have the lens, we have the principal axis. So ray 1 starting parallel to the ray axis, okay, principal axis I mean. It hit the lens, okay, it hit the lens at this point, and it's converged, okay, it's going down. To what point? It's converged, let's see here, it's converged to point F, as we see here. It's converged to point F, okay, so this is F, okay. So all the light passing through, it's converged to point F, okay. So this is ray 1, okay. Start from the object, hit the lens, okay, and then going toward point F, and then continue. That's for ray 1. What about ray 2? Ray 2, look at that. Ray 2 doesn't go parallel to the principal axis, it goes directly to the point F, to the focal point, okay. So the ray 1 going parallel first and then to the focal point. However, ray 2 going to the focal point, it hit the lens and goes parallel, okay, and then goes parallel. When these two lines, ray 1 and ray 2 meet, okay, then at this point we have the formation of the image. We have the formation of the image. Again, I repeat, so we have ray 1 and we have ray 2. Ray 1 going parallel, hit the lens and then goes to point F. Then for ray 2, okay, it going directly to the point F, okay, to the focal point, hit the lens and then goes parallel. When both those rays meet, okay, then we are talking about the image, okay. That's what they are trying to explain here in this text, okay. So it passed through the focal point after passing through the lens. So here they are discussing ray 2, okay. So ray 2 also reflects from the top of the object. Starting from the top of the object, it's passed through the focal point directly, okay, at the same side of the lens, going directly to the point F, and then after that continue parallel to the principal axis. Alright, so that was regarding the convex lens. Okay, here we are still studying the conditions of the convex lens. Sometimes also in our daily life, especially the elderly people, they use the magnifier like the one here. But how this magnifier is used or function, how it come to make the letter bigger. Okay, why we call it magnifier? Because it makes the letters bigger and more visible for the people to read. But how this happen? So it's kind of it's a kind of convex lens. Convex lens. Okay. So here, but at this condition, look at the condition here. We put the object XO, means the position of the object is between 0 and the focal point. So that's what we did here. Okay, so we have the origin O, the lens, and that's the focal point. I put the object in between. Okay, so that's the object. That's why what do we call as object. Okay, it's between the origin O and the focal point. Okay, so let's start studying or formation of the image. Okay, let's make the image together. So we have two rays. We always need two rays, ray 1 and ray 2. So for ray 1, it goes parallel, as we discussed earlier. It goes parallel. Let's draw it. Okay, it's going parallel, yes. It hit the lens and then goes directly to the point F. Okay, as discussed here. Okay, directly to point F, and it continues down. Okay, that's regarding ray 1. What about ray 2? Look at that. Ray 2, okay, it seems that it's coming from point F, from the focal point. Okay, remember, ray 2 is from focal point and then parallel to the principal axis. So ray 2 is from pretending coming, that's why we put here a pointing line. It pretend coming from the focal point. It goes directly, hit the lens. So imagine it's a big lens, hit the lens, and then it continues. Okay, it continue parallel, okay, to the principal axis. But we have a problem here. These two rays, ray 1 and ray 2, these two rays, they will never meet. So we'll not get an image. Okay, so ray 1 and ray 2, they will never meet. So what's the solution? The solution is to extend ray 1 and ray 2 on the other side of the lens. So in this side of the lens they will never meet. So the solution is to go back. Okay, so this is ray 1, I extend ray 1. Okay, that's why I put it as pointing line. Okay, it's a pointing line. Okay, it's a pointing line because it's a virtual image you will see at the end. Okay, and we extend as well ray 2, we extend it this way as well on the other side of the lens. The moment they meet, then we have a formation of the image. We have the formation of the image. All right. Okay, so that's the image. Do you notice something? The image is way bigger than the object itself, and that's why, and that's how the magnifier is working. So we have a small object, it's magnified, we have it now as bigger. That's why we see the image as bigger. Okay, and that's one of the functions of the convex lenses. That's one of the function of such lens. All right, so let's continue with the second condition. Here we are with the concave lens. This time we'll see how we can draw the object, the image from the concave lenses. So remember, the function of the concave lens is to diverge the light. Okay, keep that in mind, that the function of the concave lenses is to diverge the light. That's what they are reminding us. A concave lens causes all light to diverge. Okay, as we see here in the figure, the light, after hitting the lens, they diverge, each one going in its own way. So, as well, in this text, they are explaining to us how to draw ray 1 and how to draw ray 2. Okay, that's ray 2. So, we'll see how we will draw the image or formation of the image from this kind or this lens. Alright, so mainly we have the object. Okay, as you see, it's way away from the lens. So this is the lens and this is the object. It's positioned way from the lens. Okay, so how it works? So we need always ray 1 and ray 2. Okay, we always need these two rays to help us locate the image. Okay, so first of all we have ray 1, it's going parallel as always. It's going parallel, okay? It's going parallel to the principal axis. Okay, it hit the lens. Okay, it hit the concave lens, but it has to diverge. If it's hitting F all the way, so it's not a concave lens, because concave lens have to diverge the light. Okay, so it hit the lens and then the light have to diverge, but in what direction? It's in what direction the light have to diverge. So look at that, the light going this way, but how do we know why it's not going this way or that way up? Why specifically in that direction? So this is defined by the focal point, which is on the other side of the lens. So we extend the line, here we draw it as pointing line. Okay, it's pointing line. It seems like coming from this point F. Okay, so from this point F, we draw a pointing line, it hit the lens and then it goes directly up. Okay, that's for ray 1. Okay, what about ray 2? Ray 2, the same thing, it goes directly to the point F, to the focal point. It seems going the focal point F, but the moment it hit the lens, here no problem. It could be it could hit this focal point or that focal point, doesn't make sense. So ray 2 going and hit this focal point, okay, but cannot reach it. Okay, so after directing ray 2 to the focal point, the moment it hit the lens, it goes parallel to the principal axis. So here it's going parallel to the principal axis. But also similarly in this zone, we don't have a formation of the image, because ray 1 and ray 2, they will never meet. So this is ray 1 and ray 2, they will never meet. So what's the solution in this case? As well, we have to extend ray 1 and ray 2 on the other side. So we make this pointing line and that pointing line. The moment or the place they meet, so this is the formation of the image. Here it is. Of course, it's virtual image. It's a virtual image because it's before the lens. Okay, so it's virtual, and as you notice, it's way smaller when compared to the object. So the object is a big size, whereas the image is a small size. Okay, one important idea to mention here before moving to the next slide. The sight lines, okay, of ray 1 and ray 2 intersect on the same side of the lens. Okay, this is the same side of the lens. They will never meet in this area. Okay, so the image, as you notice, is upright. It's standing, it's upright, it's the same direction they mean as the object, and smaller than the object. Okay, and smaller than the object. Alright, so let's move on to our next slide. Now talking about the equations. Okay, lenses equation. Okay, so entering the second part of the lesson. Okay, so for those lenses we have some equation to keep in mind. Okay, the famous equation is 1 over f. Let's write it here because we'll use it in the application. So it's 1 over f. I mean by f, the focal point of the lens is equal to 1 over xi, which is the position of the image, xi. So 1 over xi, I stands for the image, and x represents the distance from the lens to the image. Okay, plus 1 over xo. 1 over xo, and again O stands for the object. So it's the distance, x is the distance from the lens to the object. So this is the equation to keep in mind when we are trying to solve the equation. Okay, and one more idea here before moving. In case of virtual images, they are always have on the same side of the lens. Okay, as we discussed earlier. Okay, virtual images, they are on the always the same side of the lens. Okay, that's why they are virtual as well, which means the image position is negative. So the image position in case of virtual, xi is supposed to be a negative value. Okay, keep that in mind. Okay, one more idea we notice also, and we'll discuss this later in the table that we'll see. So notice that a concave lens produces only a virtual image. Okay, we'll see, I will show you a table in a bit, that concave lens always producing virtual images. Okay, whereas a convex lens sometimes produce real, sometimes virtual images. Alright, let's keep on. And that's the table that I'm talking about here. Okay, before discussing this tree, let's look at the table first. Okay, it's an important slide to discuss. So, in this table, look at that. Okay, we are studying the convex, okay, and the concave lens. So as you notice here, the concave lens always is giving us virtual image. Okay, so if you look at the table, the concave is always producing virtual image, whereas, okay, it's always reduced. Okay, the image is always reduced. Okay, it means have a small size when compared to the object. Okay, and the position of the object is always bigger than xo. Okay, and the focal point, this is the most important as well, the focal point is always negative. So concave, in concave lens, always producing virtual image, the image is reduced always, and the focal point f is negative when we apply this equation. We'll see later. In case of convex lens, as sometimes producing real, sometimes virtual images. Okay, as you see, we have the two cases. This depends on the condition. If the if the object position is bigger than 2f, double the focal point. Okay, so we have a real image. Okay, or if it's between f and 2f, okay, also producing a real image. It could produce virtual image in case of, as we saw earlier, if the object is positioned between the lens, between O and the focal point. So keep that table in mind. Okay, it will help us solving the questions. It's also summarized using this tree. Okay, we use this tree as well to summarize this table. So the lenses are two types. The concave, that's a mind map. Okay, it's a concave or convex. Concave or convex, yes. In case of concave, always producing a virtual image, whereas in case of convex, sometimes real and sometimes producing virtual image. Again, this depends on the conditions. Okay, these are the conditions. So depends on the position of the object. Okay, so the virtual image, okay, it's giving us a larger image, sometimes giving us a smaller image. Okay, comparing it to the object. All right, we continue. Here we are. Okay, so again the focal point. Okay, this image also telling us that the focal point in case of this kind of lenses is always negative, because it's on this side of the lens. So that's why we consider when we calculate that the focal point having a negative value. Okay, let's see it together here. Okay, so the sign convention. So this means that all the scientists or the physicists, they agree on that for focal length is different than from a convex lens. So the position, okay, for the focal point of the concave lens is different than the one in the convex lens. So if the focal point of a convex lens is 24 centimeter from the lens, we should add a negative. Okay, so that's a convention. Okay, that's how they agree together, that the focal point in case of concave lens, okay, have to be negative value minus 24, because it's on this side of the lens. Okay, that's an important equation that will be used later when we are solving the questions. Okay, here we are with another equation about the magnification. M stands for the magnification, and it represents the comparison between the height of the image and the height of the object. Also, it's related also to the position of the image and the position of the object. So let's keep this equation in mind. So M equal to HI over HO, which is equal to minus, okay, XI over XO. So we'll keep these two equations for later application. Okay, so here we are with the first application. So an image formed by a convex lens. So here we are talking again about a convex lens. Okay, so an object is placed 32 centimeters from a convex lens. So that's the position. Here is the object positioned 32 centimeters from the lens. Okay, that has a focal point of 8 centimeters. So the position of the F is 8 centimeters. Okay, where is the image? So they are asking about XI. Okay, so let's solve this example together. Okay, so let's first let's write the known and the unknown of this question. So we have the position of the object, which is XO. In this case, it's equal to 32 centimeters. Okay, which is equal to as well 0.32 meter. Okay, but no problem, you can keep everything in centimeter here, because we'll measure the XI also in centimeter. That's not a problem here. Okay, that has a focal length of 8 centimeters. So F is also 8 expressed in centimeter. And the question is, where is the image? So they're looking for the position of the image, XI. So let's refer back to this equation where XI is the unknown. Okay, you can use your shift solve on the calculators, or you can write that XI equal, it's equal, after we arrange it, it's F multiplied by X0 over X0 minus F. So after you replace those numbers, okay, so F, which is 8 multiplied by 32 over 32 minus 8, you'll get like 11 centimeters. So the position of the image is 11. It makes sense because the object is 32. It's a big area here, big distance, 32. So I get 11 only on the other side, which seems to be smaller, so 11 centimeter. All right, let's move on to, that was for part A. Okay, so B, if the object is 3 centimeter height, here we are studying about the height. Okay, if the object is 3 centimeter height, so I mean by HO is 3 centimeter. Okay, how tall is the image? Again, HI is the unknown. Okay, so HI is the unknown, but I still know XI and XO, so I can replace it in this equation. So to arrange it, so HI will be equal to H0 multiplied by XI, don't forget the negative, okay, over XO. So you can arrange, I mean you can replace those letters by their values, and you get the value which is minus 1 centimeter. So let's continue with part C. What is the orientation of the image? So because we get a negative value, so this means the orientation is opposite to the object. So as you see here, the object orientation is upward, as you see here, but the image is downward. Okay, so that's represented by this negative here. So what the orientation of the image? The image of the orientation is downward. So you can write it down here, it's downward. Okay, that's it for this slide. Let's move on. Next slide. Here, let's go with question 15. Okay, so a 2.25 tall object. Okay, so HO is given in this case. Okay, HO is given. So this is 15. Okay, which is 2.25 centimeter. Okay, is 8.5 centimeter to the left of a convex lens. So its position XO is 8.5 centimeter from the lens. Okay, this means the object position. Okay, 8.6 to the left convex lens of 5.5 focal point. So F, the focal point, is 5.5 centimeters. Okay, find the image position. So the image position, which is XI. All right, so that's what we need to calculate here. So it will be equal to x0 multiplied by f, if you can arrange the equation, over x0 minus f. You can do the replacement and you get like it's 15.6 centimeter. All right, moving on with the defects of spherical lenses. As you know, not all lenses are perfect. Sometimes we have problems with the lenses. Not all of them are perfect, and sometimes they don't give us a very clear image. Okay, so this is because of defects. Defects means errors or mistakes in the lens itself. Okay, so let's discuss this. So in reality, the spherical lens, just like the spherical mirrors, have intrinsic defects. They have mistakes or errors that cause problems with the focus and the color of the image. The two most famous defects of the spherical lenses are the spherical aberration. Okay, first one is the spherical aberration. Okay, I want you to look at comparing these two figures here. Okay, taking from two different lenses or cameras, you see how much this picture is net and clear. Okay, the same image and the same object get pictured. Okay, but here it's a little bit flu. Okay, it's not clear totally when compared to this image. Okay, and that's what we mean by spherical aberration. This is caused by a main reason, which is the position of the focal point. Okay, as you see here, okay, for a clear lens, okay, for a clear net image, okay, of a lens, okay, having a specific position of the focal point. Whereas sometimes some lenses, they don't have such function, okay, that ability, that their focal length, okay, is distributed. Okay, it's not only in a single. All right, that the lens is diverged, okay, to a single spot, but that single spot is dispersed on the principal axis. As you see here, you don't have a very concentrated focal point, and this is caused, this image, okay, it's not clear. This is caused by such a problem, which is the spherical aberration. So in reality, parallel rays that pass through the edges of a spherical lens focus at positions different from those of parallel rays that pass through the center. So not all the rays passing through the lens come to a single point, okay, causing this kind of problem. Okay, so this inability of spherical lenses of focus all parallel rays to a single point is called the spherical aberration. So that's the first problem. Okay, talking about the spherical aberration. Okay, the next one is the chromatic aberration, as you see here. Okay, I am sure that all of us saw such a problem before, when the light, not all the light, because the light disperse, the red color is different from the blue color. Okay, this is causing something called the chromatic aberration. Okay, so because every color have different wavelengths, so different wavelengths of light are refracted at slightly different angles. So as you see here, the angle of the red light is different from the angle of the blue light, and as a result, they disperse in a single or in different position, causing such problem, okay, called by chromatic aberration. All right, let's move on. Okay, thank you for attention, and that's it for this chapter, and see you in the next part on the application of lenses.